Thanks for coming. This is Advanced Debugging Techniques for LabVIEW FPGA. I'm John Gentile. I'm the FlexRio Product Support Engineer at National Instruments, as well as also the high-speed serial devices.
Hello, I'm Jim Kneale from Northrop Grumman. I'm an advisory engineer and have been using FlexRio for a while. We'd like to share some techniques that have gotten us both out of trouble, and hopefully they'll do the same for you. There's some unique challenges when you're debugging an FPGA design. The main thing is that you can't probe it. It's not running on the host PC. You can't see all the controls and indicators. It may be running at a lot higher clock rate, and you can't see that on your display. If I wanted to go directly into the hardware with an oscilloscope, most modern FPGAs are all grid arrays. The signals aren't present on the external pins. Once you start running into the hundreds of megahertz, the signal integrity may be an issue as well. It may work fine in the debugger, it may work fine in the lab, and then you get it out into the field, and you've got longer cables, and that reality is going to bite you. Also, FPGAs tend to have a lot of complex logic and state machines in there, and sometimes it can be troublesome to make that transition from LabVIEW for Windows to LabVIEW FPGA. It's a different mindset, and there's a learning curve. They haven't had this product out for that long, and there's a lot of people who are really good in LabVIEW, and there's a learning curve. If the design was easy, I'd be using a waveform generator, but we go to FPGAs when we need to push the envelope. If you can manage the impact of these errors and correct them faster than your competitors, then you win.
Okay, so first we'll go over some initial debug techniques, and we'll kind of progress through this presentation from, I'd say, simplest to most complex. And I think it's good to keep in mind, too, that each one is its own tool, and you keep it kind of in your toolbox, right? So you use which one is the best tool for the job at any given time. And so we'll be going over the different types of tools to have a goal of identifying a fault in an FPGA design, and then ways to get around that fault or fix it. So as an intro, who here has had trouble with FPGA designs, and what kind of faults have you guys seen before?
I just had trouble.
Just trouble? Yeah.
Had some issues when crossing clock domains.
That's it.
Some kind of hand shading behind the loop.
For sure, crossing clock domains is a big one. Other than that, see anything?
Yeah, making sure that when you shut down the reel, that everything's shutting down.
For sure. Yeah, those are all really good examples. And for example, some of the ones are, what if you don't have a trigger that's not arriving? Or you have data maybe flowing to your host processor, but it doesn't look right at all. It's not what you expected. So it's good to keep these kind of errant behaviors in mind for what the intended tools, again, that we're going to be tackling here. Cool. So I'd like to start with the very first one, which is actually simulation. So simulation is also good if even before you have a design that's going to compile. So for example, when I'm just trying to develop a new, whether it be algorithm or FPGA design, LabVIEW has the nice feature of that LabVIEW FPGA is very similar to G host code, right? So a lot of times it's useful just to prototype your design in a host code VI and see if the general design of it works, right? And then as well, LabVIEW FPGA has some nice hooks that actually, when you have a LabVIEW FPGA VI, to simulate it with both simulated I/O as well as also simulated timing between the different LabVIEW FPGA interfaces you drop down. And then taking it one step further, depending on what your design, again, you're calling for, usually it's if you have a LabVIEW FPGA design that has some maybe VHDL or Verilog IP as part of it, or maybe some custom clip, then you may be interested in more of the into more of the advanced simulation, what I call. So that's the third-party simulations that integrate with LabVIEW FPGA. So that's, for example, we have tutorials online for using Xilinx iSim and Mentor Graphics Model Sim. And so, for example, that's kind of like the waveform graph you could see to get cycle-accurate timing. And the only caveat, though, is it does require some more advanced techniques to actually test it. So if any of you guys are familiar with, I guess, traditional FPGA design where you create a HDL test bench, that's going to be your similar flow from there. So point in case, it's a very good initial debug step to even make sure in theory, your design is running correctly. So let's say you simulated or you made some host code VIs, and for the most part, it looks like what you've designed is going to work. Then your next step is what probably every person in this room has experienced at some time, which is getting it to build. So this is a very common, obviously, problem, whether it be a timing violation, right? You have a path that's just too long in between logic, or you have too high of a clock rate, or if you have too many resources, right? Because in FPGA you have limited fabric to work with. At some point or another, you're going to run into a compile error. But I wanted to bring this up to keep in mind that what we're going to be talking about today in the presentation are tools to debug a design that's already compiled. So let's assume for now that you have a design that is simulated and can compile. But if you are a person that is frequently running into compile errors or issues, we do also have resources online to help in that sense, like how to debug a timing violation. And I'll do a quick plug for the high throughput LabVIEW FPGA Designer's Guide, which is a PDF you guys can find online as well too. So I think that does a pretty excellent job of going through some of the basics. So anyway, so we have a design that theoretically works, and we got it to build. But at this point, we still have, again, these errant data, or again, triggers not arriving, some of the things you guys said before. So from there, the next logical step is, well, let's break it down into the logical state machine, or the logical state diagram of whatever we're working with. And if your FPGA design is already broken into a finite state machine, this process may be a little easier. But I like to take it from the same point of what you would with basic host PC debugging, is divide and conquer. What is the most likely cause of error? Narrow it down, and then from there, maybe it's interesting just to throw down a controller indicator and maybe control the state. So for example, here's like your basic state machine with stuff in it. Or kind of like how you would in a basic hardware design, you probe certain data paths and see what kind of error or what kind of data is flowing through. Is the trigger in fact flowing from some point? So sometimes just a basic control and indicator can actually resolve, well not resolve, but point out what's happening fairly quickly. For example, what do you guys think would be a good thing to drop down if you thought maybe one of your clocks wasn't running?
Tick count.
Yep, counter. Yeah, because the counter it's easy if it counts up, right? You should at least have some clock running. So again, if we're talking about just the initial level stuff, controls and indicators are sometimes enough to do the little weird stuff. But for the most part, right, this isn't enough. We have fast toggling data paths. We have situations where we want to know every single data sample going through a data path, or there may be complex states that resolve into another state. So for example, it may not be enough to just control what state you're in. So with that, we'll hand it over to Jim, and Jim's experience with, we'll go through also some of your stuff too. So.
Yep. There's a time when, if you're trying to remain competitive as a software developer, engineering company, you need to be constantly innovating. When you're doing that, you're going to come across issues that stop you dead in your tracks. You go through all the methods in the previous slide, add some controls and indicators, talk to your application engineer, But sometimes that doesn't work either. At that point, you're going to be called into a meeting and asked these kinds of questions. What do you say? When you've got a customer, a boss, a venture capitalist asking you these questions, you need an answer that is going to give them what they want. The techniques that we're going to talk about give you a way to, with a finite amount of work, to give you a powerful tool that will allow you to tell them, yeah, I'll get it done I'll get it done in a couple of days after I put the time in to write or implement these tools. So the first thing we're going to do is look at a LabVIEW logic analyzer that you can kind of build yourself using the basic programming skills that you already know when you did your LabVIEW FPGA code and a little bit of LabVIEW for Windows. The general idea is that we put a monitor port on our VIs of interest, which is like an unsigned 32. We send that data over to the host PC with a DMA FIFO, and then we plot it using this digital waveform control, which is a really powerful tool in LabVIEW for Windows. It lets you throw the data up there, makes it all nice and pretty, shows you where ones and zeros are, and it also gives you the capability to zoom in on it. So I might capture 1024 points of data, and I can zoom in at just that spot where things are going haywire. But you can do that. With your real-time data while the unit is in the system doing its thing. Getting into some of the details, the first thing I do is any of my VIs that are moderately complex that I think I might have problems with, I put a monitor port on them, an extra pin that's only used for this purpose. I'll leave it in there for the final design because it will probably get optimized out. But you take in this case, you take the state and put it in the lowest bits, and then take any other signals of interest, up to 30, in our case 32 bits. You stack them all together into one long number by using the bit shift icon and then the adder, and then in your final VI icon, you show that little monitor port down at the bottom. I use a special case for the state of a state machine in the least significant bits so that I've got a standard way to set up triggering. When the state of that VI goes from idle to something else, that state will go from 0 to something else, and I can detect that and trigger the data collection to occur at that time, or slightly before that time. Once you have a bunch of VIs with these monitor ports on them, you can't look at them all at the same time on your host PC. You have to have some way of selecting the data and triggering on it. And so I have a little case statement in there. This code to the left is what we're working on, and those are our monitor ports coming into there. And that case statement allows me to select from the host VI, or from the host application over a control, exactly which VI I want to look at. Now there's some power in that you can add all these monitor ports to a whole bunch of different VIs, compile one time, and then when you're debugging, you can say, okay, I got the top VI to the point where I know what the problem is. Now I'm going to go to the next VI and go through that, and then to the next, and get all your problems worked out, and then recompile. So it will save you some time doing that. Another thing this does is it handles the triggering. There's some cases where you may want to trigger on the state going from idle to something else, or you may want to trigger on some aberration. But each of these cases gives you a specific trigger for that instance that you're trying to debug. Also, in the lower right hand, there's that feedback, or that little memory of 3 states. That lets me see the data 3 states before it triggered, once I get it into the host PC. And that's kind of powerful too, in case your state machine is kicking off at the wrong time. The icon that's at the far left, that thing that says logic, that's a logic analyzer, and that'll be covered in this next slide. Oh, one other point is one advantage of having the same triggering condition for each one of these VIs is that when I'm making these cases, I can just say, okay, duplicate, 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 and it'll have all that default triggering in there for each VI. Yes?
Is that shift register that you have at the bottom right implemented in logic, or is there an option to put it in memory if you wanted a bigger buffer just back quickly?
You could put it in. I'm not exactly sure how they implement it. I assume that it's simple logic on there. It's a standard FPGA control, but you could put it in memory. We're collecting 1024 bytes of data, so you could, it's roll your own. Do what you want with it. Once we get the data selected, this is what that little logic analyzer icon looks like. We have two states, one where it's waiting for the trigger from the VI that we're looking at, and then the next one, it starts collecting data. In this case, it's pretty simple. There's a lot more elegant ways of doing this, but this all fits on one slide, so it'll get the idea across. In this case, we're taking our trigger and then taking in a fixed number of samples. In my case, 1024 is what I've found useful. Once we have enough samples, it feeds it to the, it continuously streams it on a DMA to the host until it reaches 1024 and then it stops. There's not a whole lot of interactive control with this. It started out being just to solve a specific problem. You can make it as fancy as you want. Finally, getting over onto the onto the host side, most of this diagram is what would already be there. Opening up your FPGA, handling your event, and then feeding. You also have this logic analyzer going on where it's looking for anything that came across the DMA FIFO. Once we get enough bits, it reads the data, and then that little icon to the far right corner, that little tiny green thing is where all that power is with that digital waveform graph. We feed it into there, and then we display it on the front panel of our host VI. Once we're all done with the troubleshooting, we can delete all that stuff. We can delete that, but it's there for when you're in debug. You can also use this for doing unit testing on your VIs as well. When you do go to take all this stuff out, because everything is working fantastic, you do want to leave those monitor ports on the VIs that you added. Number one, if you take them out, you're going to have to mess around with all these broken wires from the monitor ports not being there. And number two is it'll probably, if they're not connected to anything or they're not used, it'll probably get optimized out during place and route. So it's not going to cost you anything to leave them there. And then if you use that VI in another application someplace else, maybe it'll give you problems there. But my VIs have these monitor ports all over the place, and some of them I use, some of them I don't. You mentioned multiple problems with multiple clock domains. I feel your pain on that. We had an issue where I wasn't getting an external clock on my clock domain, or on one of my single cycle time loops, and it shut down, and I used this technique to go after that. And then figured out later that I could have just used a counter like what John suggested. Well, but this worked too. The thing that you want to do is pass data between them using a FIFO. That way, if you have a slower clock domain and you pass it over to the faster clock domain with a FIFO, it coordinates it. They don't have to be all time aligned. You've got one port clocking into the FIFO, one port clocking out of the FIFO, and that's an established way of handling that. You want to put your logic analyzer in the fastest time domain because that'll give you the highest resolution. Also, if your clocks are not exactly aligned, you're going to get your samples lining up to whatever that fastest clock domain is. So you won't be exact, but it'll be close enough for troubleshooting. If you use this in simulation mode, be aware that two single cycle time loops running at different clocks will be simulated as being at the same clock rate. So you're going to get something that would essentially be two similar square waves where it says 10 megahertz and 40 megahertz. So just something to be aware of. The earlier versions of LabVIEW that I developed this on, they didn't simulate the DMA FIFO, so I didn't even know this thing would work until I started running it in LabVIEW 2016, and it was, wow, this is neat, I can do that.
Question.
Yes?
Did I hear you correctly that if you were to simulate this VI right now, both loop would actually be simulated at the exact same frequency?
Correct, yes. Yeah, I mean, I assume that they're working on that, but it's, you know, if this loop was running at an external clock, the simulator would have no idea what that thing is doing. So it's.
I think I'm not sure what version of LabVIEW you're using. I think we now simulate those at the relative rates. Right?
Okay.
For the last couple of versions.
Okay. Yeah, that's great. I know that as each version moves on, these simulations get more and more powerful. Finally, I tend to do most of my post-programming in Lab Windows CBI, unlike many, for a number of reasons. And I have problems when I get this thing connected up to our hardware where I would really like to see this logic analyzer in there. I'll use LabVIEW to do my integration, my early integration, but when I'm finally talking to the hardware, I'm in C. CVI also has a digital waveform graph. It's nowhere near as powerful as the one that's in LabVIEW, but it's pretty good. And so I just took the same data using the CAPI, passed it across to C, and then displayed it with a digital waveform graph in CVI. I had to add my own zoom controls on the thing. It doesn't have that capability, but it's good enough to troubleshoot some problems and solve some issues. You can also take the data and just store it into an array, store it into a file, use it for test cases. You know, once you have this array of samples, you can do anything with it. This all started out as throwaway code to fix a problem that was kicking my tail for about 2 weeks. And I was getting those questions that were on that initial slide with the managers asking. And this was the solution that I used. However, instead of throwing it away, I kind of evolved it. I made things fancier and fancier, more powerful, and it's become an important tool in my box of tricks. However, it may not be good enough. And so,
take it away. Thanks, sir. Yeah, so I think Jim's logic analyzer is a very powerful tool. And again, talking about the right tool for the tool, right tool in your toolbox for the job or the problem. Again, if you're in a fully LabVIEW FPGA design, I think the LabVIEW logic analyzer gets pretty much, it's the nice base layer that you can, again, that Jim was saying, you can iterate on if you need to, but it's also because of the use of like DMA FIFOs, it's lossless for whatever data you're trying to debug or find, whereas again, back in my initial debugging, controls and indicators, as you guys have probably seen, can only update as fast as the host can pull it, so it's not lossless by any means. So, but kind of then it gets to the next point, and I alluded to this in the beginning too. Some people, and you guys probably in this room too, some parts or possibly even the majority of their design is not in LabVIEW FPGA. You could be utilizing, again, the LabVIEW FPGA features of the IP integration node, where you have some Verilog or VHDL, some algorithm that you're trying to integrate, or, for example, some component level IP. So, for example, if any of you guys work with our high-speed serial devices, you probably fall into that bucket pretty often to do your own line protocol or communication protocol, what have you, that you're trying to integrate with. So that's when it gets a little hairy, right? It's hard from a LabVIEW FPGA perspective to, one, even touch those signals, but two, to debug them. So in these next slides we're going to go into, we're going to talk about debugging deeper. But it's good to keep in mind that these now tools are targeted for when you have a design that has this some or majority parts in hardware design language, or some, again, these lower level components. So as an intro though, the industry de facto for doing this has been JTAG for a while. So quick raise of hands, how many people have used JTAG before? Cool, good amount of you. So as a quick history lesson for those of you who don't know anything about JTAG and what this weird acronym is, it was formulated by the Joint Test Action Group as a way for, as even Jim said in the beginning of the slides, one of the hardest parts of FPGAs and modern ASICs, right, are that they usually come in a BGA form factor package, right? It's not easy anymore to throw down some physical probes and scope out what the actual physical signals are. And it initially came as a step in manufacturing or post-manufacturing to validate that the package you manufactured or threw down on a PCB actually worked, right? So it first started with this thing called boundary scan to make sure that you don't have any shorts or open circuits on the actual physical package. And the standard actually evolved into having more and more features and components that allowed you to actually, at a very low level, touch and debug, monitor, send data to various parts of your design, whether that be in again, a physical hard ASIC or in like software designs such as an FPGA. So here you can see RT photo I took of a 7 Series Flex Rio. So as you can see, the VGAs are extremely small, so there's no way you're going to be able to probe those physically. And again, you can see the general abstraction of what a boundary scan register is, where you have data in, data out. It's clocked by some JTAG clock, and that is what interconnects between your core logic, right? So whatever that may be that you're trying to touch. And then usually it's controlled by a tap or test control port, what have you. And as well as JTAG is also kind of powerful because you can daisy chain devices, such as what the right diagram is showing. Excuse me. So yes, JTAG has been the industry standard. So how do you actually integrate that on an FPGA, though? So the current, or I guess what Xilinx has for a while, and again, Xilinx is a big partner of ours and what we use in a lot of our FPGA designs, is they have a thing called the ILA, or Integrated Logic Analyzer. So this is actually an IP core that you can use to, again, control these boundary scan registers, again, connect some logic you're trying to touch, and as well, it acts as that arbiter or control for whatever JTAG interface you're trying to connect with to an FPGA. So there's many different ways to actually make this ILA core and to integrate it in your design, so I don't want to get too much into that. There's a lot of Xilinx manuals and debugging tutorials, as well as there's actually some stuff, and I'll show you in a little bit, that we have that go over the creation of it. But for the most part then, for example, if you look at this picture I have, it's of a Flex Rio with one of our adapter modules on the front of it, and it has an HDMI aux DIO connector, so for digital input and output. And so that's used to actually pipe the JTAG signals out of the FPGA design and attach to a physical JTAG debugger, as you can see here, the Xilinx platform cable USB. So it's not necessarily the prettiest, I guess, in wiring, but it definitely gets the job done, and it allows you to connect to all your traditional JTAG debugging tools, whether that be ChipScope or a Vivado hardware manager, or any of the litany of other third-party JTAG connection and debugging analyzers. And as you can see too, very similar to Jim's LabVIEW analyzer, where you have a digital waveform graph over time, and you can send some triggers and all the traditional stuff and maybe advanced features that you need. But as kind of alluded to, it may not be the best, especially from a wiring perspective, but what if you're using a device, whether it be NI or not, that doesn't have a physical JTAG header or any extra DIO to connect to? For the most part, you'd probably be SOL. But recently we've come across a new Xilinx technology that allows us to enable remote debugging. So with that, there's this TCP/IP wrapper that Xilinx created called Xilinx Virtual Cable. So again, it is a TCP/IP protocol that wraps up JTAG connections. And essentially, if you can run a controller, so again, a CPU device, that is bus connected to an FPGA and can run a basic TCP/IP server, you can run this protocol that allows remote connections. So again, the basic operation is you have your traditional FPGA and controller, right, that can communicate through controls, indicators, or your standard programmed I/O, and then the controller, which is running this, again, this XVC server, allows applications like ChipScope and Vivado Hardware Manager that also speak the XVC protocol to connect over a LAN connection or even over the internet if you have, again, like the proper networking, right, like port forwarding, all that kind of jazz. So it's pretty powerful. So one, it allows this JTAG debugging to devices that never could have that before, right? Again, the non-JTAG header or non-DIO ones. As well as it also, for a lot of circumstances, it's just more efficient. If you have a lot of devices, even if it's right next to you in a lab, but you just have a lot of them that you're trying to debug or use these JTAG ports for whatever your need is, sometimes it's more efficient to not have to keep cabling things up and connecting. You just open up a connection to this XVC server and connect to it that way. Or, as probably a good amount of you too have deployed systems, right? So if you have a deployed system and it's on top of a windmill, for instance, it's not too easy to go up there with a JTAG debugger and start debugging some signals. So from that instance, there's a lot of circumstances where it's just more convenient to be this network connected debugging. And yeah, so if for example you see here like a controller for FlexRio or a PXI controller with a FlexRio or other FPGA target in it, it opens up a lot more of those targets. So I'll give a brief overview of the process, and then we'll actually jump into a demo. So that way you can actually see it kind of real time here. So the basic overview, again, of what this process is if you were to integrate this into your design. And actually, first off, I'll plug, if you guys want to do this yourselves or read more about it, I created a tutorial called Remote FPGA Debugging with ChipScope, XVC, and LabVIEW. So if you search that at ni.com, you'll pull up this same exact diagram, and all the example code is available for you to play around with. So anyway, so your first step is to create this, the icon core, so your controller core and the ILAs, all the nitty-gritty low-level HDL stuff, right? So there's, again, I kind of mentioned this before, there's many ways to do this, and I'm not going to spend too much time to get into it. Again, the tutorial is one way, Xilinx debugging tutorials. But you want to connect it to some of your HDL logic, right? Again, this could be component level IP, IPIN, what have you. So once you have that down, and you have it integrated in LabVIEW through like the familiar clip wizard, if any of you guys have played around with that, then you can hook up the JTAG signals as basic controls and indicators, right? So that way it allows the host controller or this LabVIEW TCP server to communicate with them, as well as it's doing double duty as the actual, again, XVC server to allow remote connections to talk to these signals on hardware. Yeah, and also, it doesn't have to be in LabVIEW. This could also be a C program, right, that's using the FPGA C API interface. So you have some flexibility on that end as well. And then finally, once that XVC server is running and open, you can connect to it with your program of choice as long as it supports that XVC protocol. So here again, you see a ChipScope interface. So, with that.
Will it work on real time? So you can have it on a compact Rio?
Yes, we have tried that. Yes. So as long as, again, the two main pre-requirements really for it are the controller has to be bus connected. So when I say bus, usually like with a PXI Express backplane or in a compact Rio, right? It's integrated, and the ability for it to run a server of some sort. So
Is any particular operating system limited? You have to be a Linux or?
Not that I know of, but so for example, that's kind of what's saying like the CAPI. As long as it can run this, and it's a very basic TCP/IP server, and I'll get through actually the demo too. But as long as it can run that host code that can connect to and communicate with FPGA signals, then should be good.
When do we have a license for LabVIEW FPGA? Do we have access to chipscope, or is it extra?
It actually compiles. Other good question too. I'll show you how to launch chipscope. It comes with the Xilinx compile tool chains. So you know how that's like an add-on to LabVIEW FPGA? It's a separate install. But I believe it's similar activation process, right? Like I guess if you have SSP, it might come with it. So
Yeah, that tool chain is included with the LabVIEW FPGA license.
yeah, cool. So yeah, so we'll get into how to launch that right. Yeah, right now. Okay, cool. So let me switch this up. Okay. So in the spirit of being remote, I'm actually VPN'd into the NI local area network right now, and this is actually a controller running on my desk. So true to the XVC stuff here. But anyway, so let's start with, here I have a demo LabVIEW project that has a, as you can see here, a 6592, so a high-speed serial target. In this, it's a 1082 chassis. And so here, if anyone's not seen the clip as part of the LabVIEW FPGA project, this is it. As you can see here, here's your 4 JTAG signals, and here's some other trigger signals that we hook up to points of interest. So, cool. So in this example, have some very basic logic going on, just for, again, example purposes. You have kind of almost like a counter going on, just iterating up, some logic toggling, and yep, so just some basic LabVIEW FPGA to get the point across, as well as these are the 4 main JTAG signals, again, that's going to touch the clip and the controller core that we instantiated beforehand. So, and then here is our example server code. So in LabVIEW, we pretty much wrapped it up into just a nice interface. And again, this is all in that example that I plugged before that's online. So you can open up just a basic TCP listener connection. Here we're actually communicating with the device itself, as well as arbitrating the TCP signals. Again, I don't want to go too deep in it, but you can read more about it later. Oh. And then it'll run until you say stop, and then it'll close out a TCP connection. So let's actually select our target, and we'll run this. Cool. So now we have an XVC server running on the controller that has, again, it's bus connected to this high-speed serial device. So next thing is to actually launch chipscope. So as the gentleman in the back said, how do I actually get chipscope, right? So if you actually go, if you have the Xilinx compile toolchain installed, although chipscope is part of the older ISE toolchain, so you need an ISE toolchain installed. If you go to NIFPGA, programs, here we go. This is exciting stuff. And forgot the name of it. Cool. So analyzer.exe. All right. Here's chipscope. And so again, this is a full version of chipscope that actually comes with the Xilinx compile tools. And to actually open up a connection, it's similar as your JTAG pull-down menu, except you go to Open Plugin, and actually here, nice, it already remembered my stuff that how to connect to it. So here, the protocol type is Xilinx XVC. Host is localhost, so I'm just doing a loop back on this local controller. And if you do OK, it immediately pops up and it found our target. So there's the Kintex 7410T FPGA that's running on that high-speed serial device. So click OK. And you can see here, so it doesn't run anything when you just click OK. It just opens up a connection. So just to go over some of the basics of chipscope, this is what will be your waveform graph and show the data points that you have. You can configure different triggers or Boolean triggers. So for certain conditions that you want it to trigger on, certain capture settings or how deep of a capture you want to get. And here again you can see the device is connected. And here actually you can import signal maps. So for example, what you'll see in a second is a lot of data streaming, but if you want to convert that to, for example, an actual physical waveform, for example, like if it's ADC data that you're reading and you want it to graph, there's hooks in chipscope and also Vivado Hardware Manager to graph whatever kind of data you're looking for to make it a little more sense of it. So for example, in this code I'm running, as soon as I do apply settings and ARM trigger here, it's set up to immediately trigger logic on the FPGA and then send that through the JTAG header. So, cool. And here you can see all the different data ports that we configured beforehand and the signals. Zoom in, pretty cool. So we can analyze timing at a maybe more fine-grained level. And yeah, from here it's where you really get creative or whatever your debugging or test needs are. And yeah, there's a lot of powerful features in the Xilinx toolchains as well. So that's the XVC stuff. So.
I have a question.
Yeah.
Are you going to revisit, like you briefly touched base on this is a clip and now we're using it, but that's the whole thing that basically hooks into, allow you to hook with chipscope, right?
Correct.
What, are we going to expand on that or no? Or?
Well, so it's not what it's so yeah, it's different than XVC. It is what allows you to connect with JTAG. So not just chipscope, but any JTAG debugger. So it kind of gets real deep real quick, so I'm not going to really cover it too much, but it does go in depth in a tutorial that I linked, as well as some other tools. So feel free to bug me after this, and we could talk some more too about it. So,
are there any limitations to what products that can be used on?
Probably. So I don't want to say a general blanket statement and say this will work on everything. So far, what I know we've tested on is Flex Rio devices, high-speed serial devices, so pretty much Rio-based devices that allow component-level IP on a PXI target, as well as control for Flex Rio and My Rio and C Rio stuff. So, so on top of my head, I can't think of anything, but I don't want to overpromise. So. But that's also why it'd be good to use a tutorial and kind of play it out. Your mileage may vary, kind of deal.
On that real-time or the host block diagram, you had the TCP server and the FPGA reference. Do you have to like connect those together somehow, or like DMA the data up to the chip to the TCP server, or like how is that all connected? So yeah, it's actually just connected through. Yeah, I guess I'll flash it a little quick. Let's go through it. So it's just connecting with the actual controls and indicators on the design. So for example, here's the JTAG header that we're actually bit banging. So again, it's software, timing, and that's how we communicate. Bus communicating with the FPGAs. Any other questions? Cool, good questions though. Okay, so as an extension of, since we're talking about Xilinx toolchains and some more advanced features, especially for if you have people on your team that are used to VHDL or other HDL designs as part of your FPGA system. There's a new feature actually coming out in LabVIEW 2017 that this might be the only talk where we actually touch on it. So it's pretty exciting stuff.
but it's called Vivado Project Export. So what it is, new LabVIEW 2017. So it is meant for, again, the designer or team that is, again, used to design this workflow. So instead of, for example, just being able to debug a certain black box IP or your certain design in just Vivado, you're actually able to export an entire LabVIEW FPGA design into the Vivado workflow. Only caveat is our intellectual property is encrypted, so like our PCIe IP and like our DRAM stuff. So, but pretty much everything else that you design as a user or anything that you really want to touch anyway is left unencrypted and open to play with in Vivado. So really how it works is you can see it's user board support IP, user clip. It's just going to be another drop down as opposed to compilation in a Vivado a LabVIEW FPGA project. So you export to Vivado, and then it spits out a Vivado project file with all the supporting designs, and you can, some of the debugging that we talked about before, how I was saying like, oh, depending on your method, dropping down the ILA cores or JTAG connections, all that stuff, is some of that's actually pretty easy to do if you're just in a Vivado environment. So that opens up even new doors for the debugging that we talked about. But again, the benefits are you still can retain the kind of investment we've had with our intellectual property, again, of the PCIe or whatever bus architecture you're using, DRAM, other FIFO architectures. So again, it just opens up the designer to just worry about their code, but still use a Vivado workflow that they might be more comfortable with. So, so yeah, new feature. Right now it currently supports FlexRio and high-speed serial products.
How will it still end up generating this LabVIEW file so you can call it from the host, or?
I believe so, yes. So pretty much the functionality is all wrapped up to once you have a design in LabVIEW FPGA and your clip or whatever IP design you have, and you bring it into Vivado, you can continue your workflow all from there. So.
But then that has to generate, I mean.
Right, and then generate a bit file.
And then LabVIEW encapsulates this bit file, put in all the controls and indicators. And
correct. Yep. So that way, and then you can integrate it with whatever host design you have, be it, again, CAPI with FPGA CAPI or a LabVIEW host diagram. So.
We actually create a script which is embedded in the Vivado too. So after you complete your design in Vivado, you actually can get the stream of the file generated in Vivado. And then you will get the zip file and use that in the LabVIEW source VI.
Okay, that makes sense then, because then you added something that otherwise I would see missing.
Right. We actually don't have an export import way for you to get your file back to the FPGA yet. You will be able to use that file on the site.
What happens if I change the device to something that's not supported by AI?
I don't think it won't be the option I think yet. Thank you. Sure.
If you use a different tool chain, especially some of the complex high-end stuff, like where I work, a lot of times they don't talk very well, and so there's some assembly required. One thing that I noticed about NI's tools, especially with the FPGA, is it works out of the box. You don't have to mess with it. You don't need a support staff to deal with it. So sometimes, well, comparative.
Yeah. Cool. So yeah, again, FlexRio high-speed serial devices are what we're supporting first with this, but highly encourage you if you guys have, again, members or yourself that would benefit from this, try it out, and we'd love to hear what you guys are doing. With that final slide, just kind of encapsulating what we talked about. So again, I kind of foreshadowed this in the beginning, right? So each thing we talked about is another tool in your toolbox. Each one is designed for a certain problem or job that you have, and there's different degrees of complexity, and there's different times when you want to use or not use something. So pretty much going down from, again, we talked about simulation, unit testing, design and conquer, divide and conquer. Jim's LabVIEW logic analyzer. If you have more than G code, then maybe JTAG. If you don't have a physical connection, then this XVC stuff might be good for you. So, with that, any final questions?
one comment is, if you have the NI app on your phone, you can get the slides off of that, and I believe they're posted on the website. So just do a Google search on the content or on the title of any of the presentations that you'd like to see later on.
Yes, just had a comment to the last slide about simulation.
Sure.
I mean, for me, I would say that you should only do this chip level debugging when you're really sure you can't simulate it. So I think creating like really nice test benches will save you a lot of time. Instead of trying to do everything in hardware and trying to simulate a lot of things in hardware, that you could actually just write a simple PHP system.
For sure, yeah. Especially like I kind of I guess alluded to that too. If you are a person that comes from that traditional VHDL or Verilog design process, that is part of your development process, is developing the test benches, right? And then also making sure things work accordingly. So yeah, again, your mileage may vary. That might be your majority of debug time is actually in simulation and iterating on designs, right? And then yeah. So and again, that kind of hits point to even if you aren't touching HDL or Verilog and such or a chip level. It is really useful to use LabVIEW FPGA VIs or just host VIs to do that debugging, because for the most part they run, except for some fancy interfaces, the code runs similarly the same. So and you don't have to wait for a compile to happen. So utilize LabVIEW VIs as much as you can, I'd say, in your same kind of development flow. Good point. Anyone else?
The code that I put up there for the logic analyzer is fairly simple pictures. I would have loved to have, supplied it to, put it up on the website as the code, but unfortunately my employer is a large defense contractor, and if we give away code, it has, even if it's free, it has to work. In order to say that it works, it has to go through some gauntlet of tests and people and staffing, and that didn't quite happen. But you can just write look at what's on the slides, type it in yourself, and you should be fine.
Cool, awesome stuff. All right, well, if there's nothing else, thank you guys for coming. Appreciate your time.